Yes, thank you very much, Menching, and thank you very much to the organizers for the opportunity to present some of our results in this very nice conference at this very nice place. So what I would like to discuss today is some recent results that we have been obtaining on ruthenium-based materials that are quantum spin liquid candidates, or KITF quantum spin liquid candidates. So I will continue on the topic we had this afternoon, and I'm going now back to materials. And what I want to show you is also how we then try to understand these materials by doing a microscopic modeling based on ab initio. So first of all, I would like to acknowledge my collaborators, because I will be talking about two classes of ruthenium-based materials, hexagonal systems and as well as triangular systems. And this work has been done in my group in Frankfurt. David Kuyk, who has just finished his PhD, Kira Riedel, who now completely moved gears. So she was a postdoc in my group, and now she's doing climate modeling. Probably a very interesting field to move to. Alexander Ratspopov, who is also a PhD, Francisco Ferrari, who is a postdoc, and we have been collaborating with Igor Mazing, Johannes Knoller, Stefan Backers, as well as Leon Valens and Stephen Wilson on the triangular lattice systems. So let me start by the two most important papers in this field of KITF quantum materials, which have been coming many times in this conference, and therefore I shouldn't repeat again what has been said, but of course one of the important seminal works in this field is the work of Alexei Kitaev on the so-called Kitaev model, which basically consists on this bond-dependent Ising model on the honeycomb lattice, which is exactly solvable, has a C2 quantum spin liquid ground state with gapless Majorana fermions and static gap fluxes. And with an application of a magnetic field, we have a chiral spin liquid with Majorana H states. And this model, in fact, there has been a precursor to this model, which I would like to mention, which is the compass model that was discussed in the context of the Kugel-Komsky model by Kugel and Komsky. And the second paper that has been very important in this field is, of course, the work of George Jacali and Ginyat Kalulin, who were the ones that this model that looked very abstract from the point of view of how it is defined, they basically showed the recipe of how to have this model realized in materials by introducing basically the fact that what we need is to have transitional metal ions that are heavy, so where the spin-orbit coupling is strong, and then in an octahedral environment of ligand atoms that will do the crystal field splitting that is needed into T2GeG, and then by just connecting this octahedra H sharing, then what we can realize is to get rid of all these interactions that are usually the stronger ones when we have spin systems, and just have surviving these terms here, which is this tensor, symmetric tensor contributions, where we have then here the KITF contribution. So after these works, there were a large amount of materials which in fact were keeping this concept of having these honeycomb lattices, following this idea of having here the 5D or 4D 5 electron filling. So the iridates, the so-called 2,1,3 iridates, as well as alpha ruthenium trichloride, and then also other polymorphs that we have been seeing today in Radu's talk of this lithium iridate. And there has been, as Radu was showing, also 4F systems and 3D systems and other fillings where you also can realize these kind of KITF interactions. However, most of these materials, maybe except for these materials synthesized in the group of Hide Takagi, most of these materials show a ground state which it's a long-range magnetic order. So they are not genuine quantum spin liquids, and in fact, in this case, what has been pointed out. So Natalia worked a lot on that. We also worked on that, is the role of bond disorder to explain the fact that this system doesn't order at low temperatures. So why all these systems are ordering? So most of these candidates, why they show a long-range magnetic order? So of course, one of the first things that one does is, let's go back and look at the most basic elements of the description of the system. So let's look at the crystal structure. So what is exactly happening into the system? So one of the effects that is indeed in these materials is that they are not perfectly, so they don't have this perfect octahedral environment of these magnetic ions. So in fact, if we are in this perfect octahedral environment, we do have that there is the T2G, which is the orbital, so the splitting of the D levels into T2G and EG due to the octahedral environment. So what we have in this case is indeed this perfect KITF interaction when we have a strong spin-orbit coupling. However, if the systems show some distortions, and one of the most common distortions in these materials is the trigonal distortion, so basically that either the octahedra are squeezed or elongated, then what happens is indeed is that there are many more splittings in this T2G set of states, and what happens is that the orbital degrees of freedom get quenched, and we go away from the KITF either to the Heisenberg limit or to the Ising limit. And of course, the zero magnetic factor will also be anisotropic. So this already is telling us that we are going to expect, apart from KITF interactions, other interactions that due to the fact that we have this single ion anisotropy. And not only, of course, what we have in the material is that these octahedra, they are coupled, and therefore they are going to be different type of hybridizations depending on what type of ligand atoms we have in between these transition metal ions. And what I'm showing here is, for instance, the expressions of the exchange interactions obtained from perturbation theory in a multi-orbital Hubbard model, including spin-orbit coupling. And this is written as a function of the hybridization, so hopping parameters between, in this case, nearest neighbors. So these are the most important hopping processes between, so this is ruthenium-ruthenium, through the ligand atom, in the case of ruthenium trichloride through chlorine, and therefore, and then there are also the direct hopping parameters T1, T3. Now, what one can observe already from this perturbation expansion is that very small changes in these hybridizations that one can quantitatively define in terms of this angle here that I'm plotting here, very small changes in the hybridization make huge changes in your exchange interactions. So for instance, in this case, if you put the information of these hopping parameters for alpha ruthenium trichloride, you just, by distorting this angle a little bit, one can get, in fact, that these non-KITF terms, so this is the off-diagonal gamma terms, and this is the Heisenberg term, you may be able to suppress them and bring the system more into a more pure KITF. So what we see is that this, in all these KITF candidate materials, the magnetoelastic coupling is very strong. So now, what we did in recent years is to develop a method from ab initio that allows us to extract these exchange interactions for these materials. And the process that we follow, so the method is basically we perform density functional theory calculations, so electronic structure calculations. From these electronic structures, you can extract the hopping parameters, so the tight binding parameters, by doing linearization, as well as the exchange, not the exchange, but the Coulomb and Hund's coupling interactions by doing constrained RPA. And then one obtains multi-orbital relativistic models that we exactly solve with exact diagonalization on finite systems. So one obtains an exact energies, eigen energies and eigenstates. And then the last step is we basically choose, because we want a spin model, a low energy model, we choose the low energy states of these exact diagonalization results, and we project onto a spin space by defining a certain basis set. And this is the spin model that contains all the contributions that we know, so all the symmetries of the system, as well as all the possible distortions and hybridization processes. So by doing this, for instance, here what I'm showing is the minimal set of parameters that should be considered if we want to describe the properties of these materials. So for alpha ruthenium trichloride, what one obtains, and in fact there are many other groups that are also doing ab initio, so the results are consistent between many groups, is that in this material, indeed there is an important KITP interaction, which is ferromagnetic. However, there is also very important gamma contribution. So this is the other off-diagonal term that in this, we have been seeing many discussions already in this conference, that this is an important contribution that one needs to take into account to explain many of the properties of the system, as well as these two small Heisenberg interactions. And I have to say that this model, which is obtained from ab initio, with this model we can explain thermodynamic experiments, magnetization experiments, torque experiments, as well as inelastic neutron scattering experiments. So this is a rather good model to describe the observations. And you can see that, for instance, for the iridate materials, the energy scales are larger, and the reason for that is because now here one is dealing with iridium and not with ruthenium, so the spin-orbit coupling is stronger, and this is also changing the scales. So now all these systems that we show here, all these systems order and have these, so basically alpha ruthenium trichloride and sodium iridate in a zigzag long-range order. Alpha lithium iridate has a spiral order, as has been seen by Radu. So the question is, where does quantum spin liquid? So how do we now, nevertheless, these other materials that we have, can we do something with them to see whether we can push them into getting this nice state? So there are various options to do that. So here would be our system, and one option is apply a magnetic field, just suppress the long-range order, and then try to see whether one reaches, by suppressing long-range order, whether one reaches a state which is a quantum spin liquid before going into the field polarized phase. And this is the region of mostly debated in alpha ruthenium trichloride, and there were many talks and discussions. And I'm not going now to go into this direction because there is a lot of discussion still, and I think that what I would like to present here is an alternative to that. So I was showing that the magnetoelastic coupling is very strong in this system. So why don't we manipulate the magnetoelastic coupling in these materials and try to manipulate the exchange constants by manipulating the systems with strain fields? And there are various ways of doing this manipulation. Of course, the simplest one is just pressure the system, but pressuring the system is not a good idea, because when you pressure these systems, basically alpha ruthenium trichloride undergoes a phase transition into a dimerized phase, and that's it. So you just get dimers. However, there are other ways of pressurizing the system, which is in fact what it is important if you want to reach. Oh, I thought that you were showing me 5 minutes. I said it cannot be. Okay, so what you can do by basically what we know, because we're analyzing these exchange interactions in terms of all these hybridizations. We know exactly what we want to do to get purely KITP, which is we have to just do a negative type of pressure. So to do a negative type of pressure, there are various ways. You can, for instance, create heterostructures that strain the alpha ruthenium trichloride appropriately, depending on which is the substrate you are using. And there has been a lot of work, and Eric, who is here, has done a lot of work on this type of heterostructures, alpha ruthenium trichloride on graphene. But what I want to discuss today is two other types of negative pressurizing the system, which is by applying chemical pressure. And also I want to show very recent results on just monolayers of alpha ruthenium trichloride, which show very interesting surprises. So what happens with chemical substitution? So in the last 2 years, there have been a lot of, there has been some synthesis on basically, instead of considering the ruthenium trichloride, you you grow the system either with bromine or with iodine. So ruthenium bromine, this is a work by Imai and collaborators. Basically, this system is also multi-insulator. However, the big surprise is when you put an even bigger halogen, so you take iodine, and basically the observation is that the system is a metal. So what's going on here? So what we did is we went and looked into the experimental results, what they were showing us about the properties of these materials. So here what I'm plotting is the resistivity measurements as a function of temperature for these three materials. So this is the alpha ruthenium trichloride, so the resistivity as a function of temperature does show the behavior that you expect for a multi-insulator. The same is for ruthenium bromine, but however, the two sets of samples for ruthenium iodine, this is one sample comes from the group of Bob Kava, and the other sample is from the group from Japan, Imai and collaborators. So basically what they see is that the resistivity is very flat. However, if you look here at the values of the resistivity, this is really high. These are high resistivities even for a bad metal. So the question is, how good are the samples quality? So whether there could be issues of disorder and stacking fault, and we know from talking with the experimentalists that they have these issues, so that whether you have here, you are dealing with maybe metallic grain boundaries. So what we did is, let me show you maybe the susceptibility as well. So the susceptibility for the three materials, ruthenium trichloride and ruthenium bromide, it does what we expect when the system orders at low temperatures. So it shows at 7 Kelvin for the chlorine, basically a phase transition, and for the bromine, the phase transition to an ordered phase, which is also zigzag ordered phase, is at 34 Kelvin. However, if you look at the two samples of ruthenium iodine, it seems like a Pauli-like of behavior, so it's very flat. In one of the samples, there is this raising of the susceptibility, which has to do with the fact that there are some magnetic impurities. So the question is this because it's a metal? Now, if you reproduce these susceptibilities, so you try to reproduce modeling, by doing modeling these susceptibilities, the chi0 that you need in order to reproduce these susceptibilities is exactly this value. So therefore, it's not clear that this is intrinsic Pauli origin, or it has to do with the fact, again, with the sample quality. So what we did is, okay, as a calculation, you usually do a calculation for a pristine system, so perfect system. Let's assume that we have perfect ruthenium iodine, and we take, of course, the crystal structure that has been given, but that we don't have issues of vacancies or any other type of impurities. So if you take now these structures and you do an electronic structure calculation, what I'm showing here is for the three materials, basically what you find is that the systems are multi-insulators. However, the gap reduces as a function of going into larger halogen atoms. And in the case of the pristine ruthenium iodine, you are really on the verge of a metal-insulator transition. So in our case, now we assume, if we are in the pristine one, it should be in fact a an insulator. And the question is, what kind of exchanges do we expect? So spin exchange do we expect for these materials? So what I'm showing here is, in fact, an analysis of the electronic parameters just to see the evolution of the Coulomb repulsion as well as the Hund's coupling as a function of going from chlorine, bromine, and iodine, so how they change due to the fact that you also have these halogens, especially iodine, that has a strong spin-orbit coupling. And here is how the fact that, let me just point it out here, the longer range interactions or hybridizations get more and more important in the iodine due to the fact that you have iodine, which is very big. So you are going to have longer range interactions. So now we extract for these three materials, we extract the spin exchange interactions. And what is very interesting is, and let me concentrate on the ruthenium iodine, is that in this case, what happens is that this third, so it's not only important the fact that you have, let me just concentrate, for instance, on the KITF. So important KITF first neighbors, second neighbors, as well as third neighbors, but the third neighbor KITF interaction is antiferromagnetic. So it's ferromagnetic, ferromagnetic, antiferromagnetic. And then there is also an important gamma-3 term here, which is ferromagnetic. So now what we did is this defines a slightly different type of model for this ruthenium iodine. So if we analyze the ground state of this model, and we analyze that by doing exact diagonalization on 24 side clusters, now what we find is with these models that we obtain with a minimal set of parameters, up to 5 parameters, is for ruthenium chlorine, the ground state is the zigzag order. The ruthenium bromine, the ground state is the zigzag order, as you can see here in the Q vectors. However, for the ruthenium iodine, we don't find a long-range order. It could well be that it is due to the fact that we have finite, so the cluster is not big enough, and there could be Q vectors that are not in the clusters. But it could be also a hint that the fact that you have these longer range KITF interactions is inducing a spin liquid. But it would be a spin liquid of a different kind to the KITF spin liquid. So for the KITF spin liquid, we can use this plaquette operator. We know that the plaquette operator is equal to 1. So we use this plaquette operator as an order parameter to see whether the type of description for this ruthenium iodine, how large is this, or how different from 1 it is, this plaquette operator. So classically, this plaquette operator is 0.04. And for this type of model, it is about 0.29. So our conclusion is that for this, if one were to have pristine ruthenium iodine, this would be a possible candidate of a quantum spin liquid, but not of a KITF type due to these interactions, to these long-range interactions. And even what is more interesting is that this system is on the verge of a mod metal insulated transition. So the question is whether one can just play with this metal insulated transition depending on the sample quality, or depending on by modifying the system. So that means that there is still a lot to be done in these hexagonal materials. But what I would like to show is now very recent experiments by so this is done in the group of Adam Sen in University of Waterloo, Bob Hopden and Steve Winter, who was a previous postdoc in Frankfurt and now is at the Wake Forest University. So what Adam Sen did is he really managed, now it's my 5 minutes, he really managed to get alpha ruthenium trichloride monolayered. And what he does is, so he takes this monolayer, puts it into, so basically into metallic, into two, encapsulates between two metals. And then he measures by contacting this system, what he does is he does inelastic electron tunneling spectroscopy. And in inelastic electron tunneling spectroscopy, changes in the conductance gives you information of possible magnetic excitations in the system. So one thing to remember is that alpha ruthenium trichloride has an important magnetic anisotropy. So what I'm trying to show here is this magnetic anisotropy that as a function, for instance, if you put here would be to put the magnetic field parallel to the plane, and here would be to put the magnetic field perpendicular to the plane. So the fact that the gyromagnetic factor is anisotropic and the exchange anisotropy is positive, this system has a very strong easy plane anisotropy. So if one wants to go away from the zigzag long-range order in perpendicular magnetic fields, one should apply magnetic fields of 70 or 80 Teslas. So that's why most of the experiments are done by putting magnetic fields parallel to the field. However, many models are predicting very exotic phases with magnetic fields applied perpendicular to the plane. So now what the experiments from Adam showed is what he did is to do different thicknesses of alpha ruthenium trichloride, and this is the first derivative of the conductance. And what he observes is, if you are, now let me maybe show you that here I'm showing these peaks as a function of magnetic field. If you are in a 3-layer, so you see what you expect, the zigzag long range order is suppressed at about 6 to 7 Teslas, and then you enter the region that you will be partially polarized. In the 2-layer system, this behavior seems to be similar, but at a larger field. In the purely 1-layer, there is the system doesn't really, it seems that it stays in the ordered phase, even at 14 Tesla. Now he puts the magnetic field perpendicular to the monolayer, and by putting the magnetic field perpendicular, what he sees is that in the 3-layer system, basically what you expect, because you have this in-plane anisotropy, there is no change in this lower magnetic excitation. In the 2-layer, he starts to see some change, but still the magnetic interactions seem to, the magnetic excitations seem to be still the ones from the ordered state. However, in the 1-layer, it looks like the magnetic field perpendicular, he's observing the same as you observed for the bulk in the magnetic field applied parallel. So basically what he observes is as if in the 1-layer you would have a reversal of the magnetic anisotropy. So if there is a reversal, where does it come from? And what we did, in fact, so there are, on the one hand, electron diffraction measurements that find that in fact there are some distortions in the monolayer, like small ruthenium buckling, as well as the chlorine in the planes comes nearby. And if you do the calculation with these distortions, indeed what you find is that the system shows a gyromagnetic factor, which is z-axis, and the exchange anisotropy also change sign. So this would be a very interesting platform. I have 1 minute. Okay, so I go now to the triangular for 1 minute to test all these models that have been proposed for spin liquids when you apply a magnetic field perpendicular to the layer and not parallel. So I have 1 minute, and I wanted, so we had last week a very nice talk by Stephen Wilson about sodium ruthenate, a triangular lattice system, which, since you have ruthenium again, you will expect bond-dependent exchange interactions. So what we did is, and in fact this is the results that the experiments that Stephen was showing, the system is insulating, there is no magnetic ordering observed up to very low temperatures, and this is the type of inelastic neutron scattering experiment. So Stephen was talking about the quantum disordered ground states. The question is, where does this come from? There was also the discussion possible impurities, but otherwise, what are the exchange interactions in this system? So when we look at this material, electronic structure, one can find that this is a Mott insulator, that it is a well-defined pseudo-spin J effective 1/2, like in the honeycomb alpha ruthenium trichloride that I was showing to you. And when we now extract the exchange interactions by doing this various multi-step process, what is important in the triangular lattice is not only the bilinear contributions, but also the fact that you may have important ring exchange. And I'm going to talk in a moment about the ring exchange. But what is interesting is that in this material, what is very strong, it's a very strong ferromagnetic interaction, as well as antiferromagnetic heat IF. And these interactions, in fact, I know I have 0 time. These interactions promote ferromagnetism. So it's telling us that the system is very ferromagnetic. And even if we manipulate a little bit the interactions, the ferromagnetism is very robust. So can we explain the experiments with that? In fact, if you take these coupling terms, first of all, one interesting point is that the classical solution of this model would have an in-play accidental continuous degeneracy, but the quantum fluctuations is what sets the ordered moment perpendicular to the bond, as also was pointed out by Radu in the context of cobalt titanium 03. So this is now basically the comparison with experiment with the model is that what we see is that this type of model with these ferromagnetic type of interactions can show this intensity observed in experiment, and in fact this at Q equal 1, which comes from the stacking in the 3 dimensions. The 4-spin ring exchange, how important it is in this material, it has been observed that it's very important in triangular lattice systems. And here it's shown, for instance, in the kappa ET, you can explain many of their orderings by assuming this ring exchange. And this is my last slide. However, because we have here a bond-dependent triangular lattice, we not only have the contributions coming from the symmetric SU2 symmetric ring exchange, but there are also contributions coming from anisotropic ring exchange. And this is very interesting because these contributions are responsible for the fact of predicting that the ferromagnetism will tilt. So with that, I come to my conclusions. My time is over. I just wanted to mention 2 issues is that it's very interesting to steal these materials, to manipulate them by applying a strain of different types. This is a new type of maybe quantum spin liquid. And in the sodium ruthenium oxide, the importance of the anisotropic ring exchange brings a new type of interaction in the system. And we don't have an answer to the disordering effect, but definitely what we can show is that ferromagnetism is important and can explain some experiments. And I thank you for your attention.
Rosa, for the nice talk. Any questions?
Hi, Rosa.
Hi.
A lot of information, so I have several questions. I hope they are small. For the iodine, the expansion seems to be a bit dangerous because your gap is, or your effective U is small. So this effective T over U to obtain exchanges.
Oh, I don't do perturbation theory. Okay. It's a projection, so we do projection. That's why.
So is projection also dangerous?
Not as far, and this is what I wanted to show. I don't know whether I show it here. Not as far. Well, here I'm showing this. Not as far as you can show that your states. So that basically the states that you are projecting to is majority of J effective 1/2. So if we have also these pictures for the ruthenium iodine, as far as you are sure about that you can obtain from the DFT calculations, then you can do this game. If you have a lot of mixing between these states, then I agree with you. This is not a valid type of. Yeah.
Right. So the other one was in the beginning. You did talk about the angle being possibly enabling one to cancel.
Yes.
not desired terms, and somehow you were vanishing two terms at the same time, and I assume there should be at least 4 exchanges, 4 different parameters. Can you vanish all 3?
No. Okay. I was showing this was just a very simple case where we just took these 3 parameters, but no, unfortunately not.
And the last one, probably very simple. So in the sequence of materials, fluorine is missing. Is there a reason for that? Or?
I think this, we have to ask the experimentalists. This I don't know, but fluorine, of course, is extremely electronegative, and I'm not sure whether they can synthesize. I think the chemistry of fluorine is rather different from the other ones.
I mean, it's dangerous to work with, I understand, but I thought the idea is that maybe it creates a negative pressure instead of positive compared with.
Yeah, and then you are done, because then you distort the structure. So it's not good.
Thank you very much for a lot of information.
I'm sorry.
My question is also about the iodide, but a completely different one. So you said it's a bad metal, so correlated metal, right? Close to the Mott transition.
Yeah.
Is it at all feasible to do photo emission on these samples?
Well, as far as I know, it's only powder samples that they have.
And
wait a second. I think there has been, there has been some photo emission, because who was telling, no. I think Amalia was telling me that, but I'm not sure whether there has been. Amalia, is there some photo emission?
Yeah, there is a report.
Okay.
Soon, I think. There is a report of ARPA studies on this material done at diamond light source. I've seen some data.
Okay,
yeah.
so there is some data, but it's not published, so.
So it's also, I think, related to Sasha's question, but a bit different. So when you do the projection, and you said in particular for the iodine that it was close to being a metal, how do you know that the states that you're projecting to are localized, actually spin states? And
so
and what's the characteristics?
That's a very important question. So that's why you see. The protocol that because this is an important point. So the protocol that we follow in order to say something about the pristine ruthenium trichloride, because the way that you model Mott insulators in DFT is by doing this DJ plus U or whatever. So depending on the U, I can take a large U and I will always open a gap. So we follow the protocol that we calculate these interactions by doing CRPA. So these interactions, what I'm showing over there, these are all calculated from DFT, so you do constraint RPA. And therefore, I'm following a protocol and since the values for chlorine and bromine are reproducing the gaps that we know about this system, so I'm sort of rather confident that the U value that I'm showing, and therefore this gap, is not being falsified because I'm using a too large U. So the U's are all obtained ab initio following the same protocol. And as soon as you open a gap, then again, you can talk about these localized states. And what I have to say is that in this calculation, you really need to include the iodine. So the iodine is, so you cannot just make effective ruthenium, you have to include all the processes through iodine. Otherwise, you don't get that. But this is the key point. If we don't get that, then we're done. There is no localized model.
Thanks for a very nice talk. I think it might have been the next slide. I was curious about the bromide.
The bromide.
Yeah, which I gather experimentally is more ordered than the chloride.
The temperature is higher.
Yeah.
Yes.
Is it kind of clear from your parameters why it would be?
Yeah, we have. I didn't show that because then you would complain even more that I threw in too much information. Yes. So indeed, the reason why the temperature, and in fact, if you look, it's very interesting. The phase transition is not as sharp as in the ruthenium trichloride, but the reason for these temperatures indeed because of the combination of interactions that you have in the system that push the system, in fact, to order. So
so which is the driver there? Is it
the
clear
driver,
what interaction is driving the
no,
zigzag order?
The driver, or let me see it here.
Is that one, yeah.
The driver interaction, if you look at the ruthenium bromine, you see that there is a very, so I think it's in these, here, you see in the ruthenium bromine, there are all these interactions here that are not there. So these start to be important in the bromine.
I guess I was looking at it, when I looked at that one, I thought, oh, the J3 has gone down, and J3 was the one I thought was responsible for the zigzag, so I thought it ought to be better, but it's actually more ordered. But.
I have to, we have to disentangle a little bit better, but we find that this K3 here, yeah, starts to play a little bit.
So I want to ask about this original idea of negative chemical pressure.
Yes.
So negative chemical pressure, you would like, let's keep ruthenium trichloride and change the lattice constant. And you can do that probably by doing a little bit of iodine into the system. Is that a promising route, or is that not a good idea?
So you say to take negative pressure by doping with iodine?
Yes.
The problem is you start to introduce disorder depending, and your life is so that's why I think that the most promising, to be honest, and this is what the most promising way is these heterostructures, because depending on the substrate, if you manage to get a substrate that you need to blow up in all directions exactly the same, you don't want to do things like that. So, for instance, in this type of heterostructures, what we find is that the strain is equal because there is a mismatch, an important lattice mismatch, but is enough to strain this negative pressure. And this is a clean type of.
Sure. So we all don't like disorder, but can you estimate how much iodine would you need to go to the negative pressure range? Is it 1% or is it 10% to go to this preferable ruthenium trichloride lattice distances?
Yeah.
Just when you compare the lattice constant of the two materials.
I haven't done the exercise. I should look into that.
Because there are materials that can really experimentally show that they really can compensate doping by pressure and get back the old phase diagram. And so sometimes you're lucky.
Sometimes you're lucky. You're right. I should look at these numbers. I cannot tell now. Yeah.
Thanks a lot for the talk. I would just follow Lucille's question about methodology. Are you taking spin-orbit coupling, for example, in ruthenium iodide, both in ruthenium and iodide?
You need them.
Yes. In both?
In both. Okay. Yeah. Otherwise, this doesn't work. Yeah.
My question is about the change in anisotropy you show in the case of ruthenium chloride heterostructure, that it can occur in the proximity.
In the monolayer.
Yes, here in the monolayer. So there is a way to change anisotropy in proximity of a metallic system. Would that be possible also in the iodine crystal, in iodine system, if it's more metallic?
Well, of course, the point here is that what we find is that the reason that there is this reversal of anisotropy is because when you go into the monolayer, the system gets some corrugation, and this corrugation seems to change the anisotropy. So there is this and I cannot tell if you put iodine monolayer whether you will have the same type of corrugation. But I have to say that we are looking into that. that ruthenium iodine is interesting for a different reason, and it's because there the exchange, the gamma, which is the one that gives you the sign also of whether it's in plane, easy axis or easy plane, there is easy access, so it's competing, and that's why it's interesting, as you know.
So, may I ask you about sodium glutamate?
Yes.
Last topics.
Yes. Yes.
And I'm kind of wondering about susceptibility, because according to Stefan, susceptibility is like a Pauli para-like. I don't see any signature of local moment Curie magnetism in this compound. And in your scenario, can you reasonably explain those peculiar behavior of susceptibility?
Yeah. So yeah, exactly. The susceptibility, we were discussing that with Stephen, because I don't have the picture of the susceptibility here, but if we want to, I mean, what is interesting is to what kind of Curie-Weiss behavior you have in this sodium ruthenate. However, Stephen goes up to 300 Kelvin, and then at low temperatures, he gets this rising up due to the fact that there are some magnetic impurities. I mean, Leon has looked into that in more detail than me. But the problem is that for the Curie-Weiss, we would need higher temperatures to really get a good Curie-Weiss, because we have to extract this term here, and this we couldn't test.
But if that's the case, you have to get quite a large, J compared with other ruthenium oxide. Did you see that kind of signature in your calculation?
Well, in our calculations, I don't have that here, but in our calculations, you see it's a combination. It's not only that there is a large J. You see these other contributions. There is this strong, very strong gamma term, and the KITP is also not. So you have to combine all these terms into the Curie-Weiss.
Yeah, but those interaction scales is kind of less than 100K. So yeah, no reason we don't see Curie-Weiss below room temperature.
You say? So
yeah, because those are at most 10 million electron volt, 100 Kelvin, right?
Yeah.
Yeah. So like, so no reason we don't see Curie-Weiss at room temperature 300K.
Well, you see the Curie-Weiss, when you do these spin orbit coupled systems, you have to you cannot use the usual Curie-Weiss, because you have spin orbit coupling, and therefore you have to use this temperature dependent magnetic moment. So you have to do a different job than the usual one, and therefore that's why I'm saying that we did this, and we find that we don't have enough data.
Yeah.
Up to high temperatures.
And don't you consider some sort of a random singlet? Because ruthenium oxide is kind of famous for this very strong dimer formation. And,
at least the structures that we get from Stephen, they don't have any distortion. The structures is very nice triangular lattice. So he has done X-ray data, and it's very nice triangular lattice. There is no distortion there. So at least from the structural data that we have from Stephen, there is no signature of this type of distortion. So, but yes, we need to work out this susceptibility. Yeah. So in fact, Stephen was telling me that going to larger temperatures, the problem is that I don't know what happens with the sample. Something happens to the sample, but it's something to
yeah, because it's a triangular lattice, so there is a frustration. So there could be a kind of random quenching of dimer singlet. That's what I saw.
Okay, if there is no further question, I'd like to thank Rosa and all the speakers in the afternoon session.